Today we're going to have a look at building up functionality using our branches and jumping instructions. What I'd like to look at today is reducing the factorial of a bunch of numbers given to us in an array. Now if you can't remember what a factorial is for a number n, it's the number multiplied by all the numbers before it. So n times n minus 1 times n minus 2 times n minus 3. So for the number 3 it would be 3 times 2 times 1, which would give us 6. So I've got a small array up here with the numbers that we're going to use for it. They're all quite small because factorials blow up very quickly, and we only have 32 bits of memory at our hands, so we don't want to go too big because we'll run out of space. Now then I have the number, the size of the array. That's going to be my point to check to see if I've gotten to the end of the array yet. And I have a couple of other words here that we're going to use just for the sake of tidy printing. Okay, so to do this we're going to need a couple of loops. We're going to need one loop to go through the array, and we're going to need another loop to go through each number. So what I'm going to do is I'm first going to do the factorial loop. That's going to be the simplest, so let's start with that. So I need to give a meaningful label so that I know what I'm doing, and I'm going to assume that the value is going to be stored in A0 so that we can print it out. So what I'm going to do is I'm going to load the immediate value into A0 of 1. Now this is our base case, so when we get down to 1 we want to multiply the number by it and then we want to stop. If we've gotten down to 1, that's the final stage of the factorial. So this is just there so that I'm not multiplying by 0 and I just get a 0 out at the end, because that would be pretty useless. So that's the first step. Now we need to actually do the calculation of the factorial. So we do fact loop. And then what I want to start doing is I want to test to see if I'm at the right place. Now I'm going to assume some of the values, some of the numbers are stored in certain registers, so I'm going to say branch if equal to 0. So if I've subtracted down all the way to 0, then I don't want to multiply by 0, I want to get out of there. So I'm going to put a branch here. I'm going to assume that the number we're doing the factorial of is stored in T0, and if it's 0 we jump to n factorial. So if n equals 0, then done. Happy days. So now that we've got that, what we want to do is we want to multiply this number, the number in T0, by the number that's in A0. So I'm going to do multiply A0, storing in A0, multiplying by T0. So there we go, that's n times the current sum, or current product, I should say. As a mathematician I should get these words right. So that gives us n times whatever the number is so far. We're going from the top down to the bottom. And then I want to decrement n, so I always want to be getting towards the base case, which in this case is 0 or 1. So I'm going to subtract from T0, whatever's in T0, and I'm going to do 1, so that when we go through this loop the next time, n goes to n minus 1. And that's just so that we're getting closer and closer to the base case. You could think of this somewhat as like a sort of recursive definition where you always want to be moving towards the base case. That's what we always have when we're doing recursion. It's a handy thing to have in mind, especially factorial lends itself to a very nice recursive definition. Of course this isn't strictly recursive because we're not making a call to the argument, we're just looping through it, but if it helps you could think of it in a similar kind of way, in that we're moving down to the base case. So now that that's done, I just want to jump back to the top. I don't want a capital J, so I should jump back to fact loop, and that should do it. Now I want to have an end case, which is going to be the end fact, and this is just going to be printing out the number that we've calculated. So I'm going to load immediately the value into V0, and I'm going to do 1 just to print an integer out, and then we'll do a syscall, and then that's me done. But not quite, because if this is one of my loops, I need to jump back to whatever the loop is that's counting through the array. So I'm going to do jump to our loop. So that's just done the actual calculation. Now we need to embed this in the thing that's going to do the iteration through the array. Now this is going to be a little bit more cumbersome than we're used to, because I have to do a lot of fiddling about to make the printing nice. Otherwise we'll just get one massive number at the end, and that's not very good for anyone that's using this code. So we don't want to do that, but it's going to mean that our code looks a bit messy compared to some of the loops we've made so far. But to start with, I'm going to load into S1 the address of nums to get our array. And then I'm going to load into S2. I'm going to use load byte unsigned because I've specified it as a byte, so I should make sure I'm consistent. And then I'm going to start my R loop. So once we finish the factorial, we jump to here to get to the next position of the array. So we need to write code that is going to reflect that. So I'm going to say branch of equal to these two at the top here. So I'm going to say let's say my counter is an S3. This is the thing that should be counting up to the size of the array. I've not specified a variable to load into the memory yet because I don't need to. I know that S3 is going to start off at 0 when I assemble my code. So I'm just going to use that initial value of 0 for this purpose. And then I want it to be S2. So if my counter in S3 ever gets up to S2, that means we're at the end of the array and we should stop. And if that's the case, I want to jump to end. Okay, so first things first, let's find the correct offset and the correct address to find the value of the array. So it's going to be the value that's in, where should we put it? Let's put it in A1. And it's going to be from the value that's in S3. I don't want to overwrite that value because remember I'm going to be using it in every loop, so if I overwrite my index then it's not going to be very useful for me. It'll only be useful for one iteration and then it'll be gone. So we're going to shift this left by 2. This is our index times 4 because we're working with words here. Even though I've specified them as decimal numbers, they are still words and it's good to keep that in mind. So I'm going to add to A1 the value that's already in A1. And I'm going to add the address of the array. So this is me getting the address of nums at position I. So wherever we are, this is the next address. And then we should load that word. And I'm going to put it in T0 because that's what I did in the factorial loop. I assumed it was already there. So make sure that I put it in there. And A1 and brackets because this is a pointer. Now this should all be fairly familiar to you so far. This shouldn't seem like it's anything out of the ordinary. We're just going to have to do a little bit more legwork in the next part to make sure that we work properly with the factorial loop. Okay, so what I'm going to do is I'm going to increment my index. And I put my index in S3. So I can overwrite it now because this is our I++. So I'm going to add 1 to that. Oop, missed out an S. So this is I++. And now that I've done that, I've really done all of the necessary work. But the next bits of work I'm going to do are just going to make this a little bit more elegant in the way that it prints out. It's going to mean that our code looks a bit ugly, and I would probably recommend actually that you look through this code and maybe try and improve it, because there are certainly a fair few areas that could be improved. For example, I've used branch of equal to 0 in the factorial loop down at the bottom here. In fact, you really want this to stop at 1 because you're never going to multiply when n is equal to 0, and when n is equal to 1 it's not going to change the product, so you might want to think about improving this. But anyway, let's get on to improving the look of this code. So I'm going to load into v0, character new line. This is my escape character /n up here. You should by this point know that this prints out a new line. Oh no, I don't want to load that in, I want to load that in. And then I want to load in the byte unsigned to A0, sorry, of new line. I got mixed up. Remember, V0 is the type of the thing you're printing, A0 is the thing that you're printing. And then I want to do a syscall. And that should be me more or less done. Now I just want to jump to factorial. So that's it more or less there. But we need to create this end label because that's where we go to once we've run out of elements of the array. So let's do that. Now I'm printing out a new line here in this line because before I get down to the factorial loop, I want to put in a new line so that my factorial values aren't all bunched together on a line. So that's just there to print out a new line so that I can get a little bit more clarity in what's coming out. So at the end here I want to do a similar thing, because if I try and print out a little thing saying done, that's why I've got this up here. So if I try and print out done, then it will just come out right next to the number that's been last printed out by the factorial. So I want to put in a new line, then load that word in, and then print that word, and then exit. So let's see how we would do that. So I'm going to load into v0 11. Now even though I've got this up here, I can't assume that that's going to be here because it might have been overwritten down here by this value in v0 of 1. So there's every possibility that I won't have this 11, which prints out a character, in v0, so I need to do that myself. And then I'll need to load by unsigned again of a0 of new line. Then I need to do a syscall, and then I want to print out the word done. So that's a string, and the system function code for that is 4. One thing about strings is you have to load in the address. Now this is because strings can be longer than a word. MIPS will know when a word is a string is finished because of the null terminating value that we saw earlier in this week. But you need to give it the address of the word, not the word or the string, not the word. So you don't do load word, you load the address into a0 of done. Now you can see this if you go into the help menu and you look for the print string button, it'll tell you that you need to store the address. And then just do a syscall, and that's me almost done, but not quite. You might think I should finish here, but remember, if the program counter continues, it will try and then do this factorial loop. So I need to actually kill this program before it drops down and tries to do the factorial loop again. So what I'm going to do is load immediately into v0, value of 10, and syscall. Now this is the system function code for end the program or terminate the program. So now we should in theory be done. Now you'll see it's a bit of a messy program. As I say, it may be worth for revision's sake going through this and seeing if you can improve it. But let's see if this works. So before we do that, let's see what numbers we should get. We'll check the first one, 9 factorial and 7 factorial, quite big numbers. So for 5, that should be 5 times 4, which is 20, times 3, which is 60, times 2. So we should get 120. 6 should be that number times by 6, so that'll be 720. And then we should have 3 times 2 times 1, so that should be 6. And then so on and so forth. So if we get these first 3 values, we'll know that we're onto a reasonable one. We'll get a big number in here, something like 5040, I think it is, for 7. And then we'll get 2, and then another large value. So let's compile this and see what happens. Luckily, no mistakes. Now I'm going to slow down the execution speed so we can watch this bounce about between the two bits of code. So let's run it and hope for the best. So this is the factorial loop. So there we go, 120 out, and it's going back up to the top and then coming back down to do this factorial loop over and over again. So there we go, the values look good so far, and there we go, you can see it execute nicely, and we're done. So this is how you build up a little bit more complexity. Now this isn't the ideal way to do this because you have to write a lot of loops if you do this. What you might want to do is write something called a subroutine, which we'll get onto in later weeks. That'll be one of our next topics. But for the moment, this is how you might want to think about building more complexity into your MIPS programs. Anyway, I hope you found this useful. If you have any questions about anything I've covered here today, please do let me know. Thanks.